Alright, let's take a closer look at the code in this LabVIEW project. I'll begin by taking a look at the overall structure for RT main. RT main has a number of process loops, and in process loop number 1 we open a reference to the FPGA VI and get this running on the FPGA itself. Checking this option is what actually runs the VI after it's been loaded onto the FPGA. This function is required to access the default personality functions, especially express VIs such as the PWM and digital I/O. The read-write control node reads the FPGA front panel indicator. Then we do a little math on that and then display that on the front panel. This process loop is updating at 10 Hz, and it stops either on the stop button or on an error condition. We finish then by closing the reference to the FPGA VI, and with this option, then the VI shuts down at the same time as RT main. I'm using a local variable to communicate the stop button state to all of the other process loops, and for this to work you'll need to set the mechanical action to one of the switching type of modes instead of the default latch action. Process loop number 2 is our pulse width modulated output control. So this loop is polling those controls at a 10 Hz rate. Process loop number 3 is developing a square wave output where it toggles its state once every 10 milliseconds. I'm using the digital output express VI for this purpose. The shift register maintains the state of the output, and then we invert that state each time the loop runs. Again, this is a conventional loop. It's a non-deterministic loop. Process loop number 4, however, is a deterministic loop or a timed loop. This one's set up with a loop time of 10,000 microseconds, and this corresponds to also a 10 millisecond update. The structure is basically the same, it's just being piped out on a different digital output. This stop button is being pulled in process loop number 1, and its state is conveyed to all of the other process loops via the global variable. Alright, let's turn our attention to FPGA main. All of this functionality that we are looking at is part of the Academic RIO Device default FPGA personality. And we're just kind of taking a quick glance over it. It's very impressive, relatively complex. A lot of the complexity has to do with the fact that many of the pins are shared. I recommend that it's easiest to replace all of the connector C functionality and then add your own as opposed to modifying the others. So I'm using a diagram disable structure for this purpose, basically commenting out that code, and then I've replaced it with some sample code here. In this first process loop, I'm measuring the time in cycles that we detect a signal being at a high level. So the signal is coming in on this FPGA I/O node input. When we see a rising edge, we reset the counter. That starts the measurement process. When we see a falling edge, that's the conclusion of the measurement, and then we capture that value here. So we see that if the condition is not true, then we just don't do anything. And so that holds the measured value. I've also placed a 1 kilohertz oscillator generating an output from the FPGA VI. All right, let's finish up by locating the functions in their subpalettes. Boolean crossing is located right about here. And then let's jump back to RT main. The FPGA interface functions are located here. You see the open reference to the FPGA VI. Here's the read-write control node, and that's where we close the reference. The MyRIO Express VIs are located right here, MyRIO. There's pulse width modulated output, and there's the digital output. Finally, let me show you how to do the local variable. You can find this on the programming subpalette, and you select the appropriate front panel control, in this case the stop button. By default, the local variable is in write mode, but you can change that to read mode.